Right, the second video is going to be looking at Micheal Faraday. Remember in the first video we just had a quick little video and experiment where we showed that there was a connection between electric fields and magnetic fields, that we're transforming energy. We're going from electric energy to magnetic energy. Right? The law of conservation of energy says that energy neither be created nor destroyed but change into different forms, and that's what we've done here. We've changed from electrical energy to magnetic energy. Right, we've converted it from one type, or we've transformed it from one type of energy to another type of energy. And we're going to get into that principle because it's in these dot points. You can see the second one specifically where we're talking about the energy transfers and transformations. So we have transformed energy from electrical energy to magnetic energy. But we still haven't talked about what's this meaning by magnetic flux. Well, we're going to get into that in a lot more detail in the next video. And we can see here that we've got this thing called Faraday's law, and then they give you an equation for Faraday's equation. Before we get into the detail of that, we've got to get our head around the basics, and the basics were, last video, 1, electric field creates a magnetic field, right? And then this one here, Micheal Faraday explored that concept a little bit more. He said, okay, if I know that electric current can generate a magnetic current, can the reverse happen? Can a magnetic field induce or create an electric current? So we did some experiments. So let's check out in this little video here some experiments you can do in the lab to see what Micheal Faraday investigated. Let's just flip the slide. That way the video fits. All right, see you after the video. As we just saw in that previous video where we looked at the connection between electricity and magnetism by Hans Christian Ørsted, Micheal Faraday started thinking, I wonder if the opposite can be done. Can we get a magnetic field and actually induce an electric field? In other words, can we create electricity? And so he did a simple but elegant experiment, and this is what it is. He got a coil of wire, and so we're going to attach our coil of wire to our large demonstration meter here. And this meter that we've got is a meter that can do both ammeter and voltmeter. So we're going to connect the ammeter up, and when it's really sensitive we call the ammeter a galvanometer. And so we're going to measure the current in this wire. At the moment it's 0 because there's no electricity, it's not attached to a battery. But let's just do what Micheal Faraday did. He got a magnet and he moved the magnet into the coil. Let's see what happens. It's a very small deflection there. I'm not sure if you can see it, but let's see if you notice it. Now, in order to make that a bit more easier to see, let's use a larger magnet. So I've got a magnet here, and let's use our north pole, and I'm going to move my north pole into the coil. Here we go. So you can see there's a larger deflection. So we have a stronger magnet here causing a larger deflection. More current is being produced, and because more current is being produced, we're getting a larger deflection here. Let's see what happens when I move it in and stop it. Now there's no motion between the coil and the magnet here. So in order to make electricity, in order to make the needle move, we have to have relative motion between the two. Right, let's try it again. When I move it, we can see the needle is moving. But do you notice something else about the needle? Let's have a look. If I put the north pole in and then pull the north pole out, north pole in, north pole out. Do you notice that the direction of the needle is changing? That's telling us that the current is going in an opposite direction. So when I put the north pole in, it's been deflected towards the 3 on the scale, but then when I bring the north pole out, it's been deflected in the opposite direction, telling us that the current has changed direction. We're going to get to why that is the case in later videos, but let's just notice that. What about if I now turn the pole around? So the north pole caused it to be deflected towards the 3. What about if I turn it to the south pole? Let's see what happens. It gets deflected to the 2. So in other words, there's opposite direction of the current. Opposite poles produce opposite direction of the current. We will understand why that is the case later, but at the moment, let's just collect our observations. So we know that the stronger the magnet, the greater the deflection. Well, let's try and now do it at different speeds. If I was to do it slowly, it deflects, but then if I was to do it fast, and hold it properly so it doesn't hit, let's do it fast. So the faster you do it, the larger the deflection. Let's see what happens when you change the number of coils. All right, so here I have a 300 coil solenoid, 300 turns I've got. And so I've gone back to my weaker magnet because the larger one won't fit in there. So let's start with the North Pole again and let's put it in nice and slowly. Wow, look at that. It deflected quite significantly. Even though I was going slowly, in the previous example with the less number of coils, we only had a very slight deflection. But now, even going slowly with a weaker magnet, it's significantly more. So obviously the number of coils has an impact on how much electricity is produced. And we're going to find out later it's a directly proportional relationship. So let's do it faster. Once again, we can see greater deflection with the rate of change. Well, what about if we change poles? Well, as before, we put the north in, it deflects towards the left. If I turn it around the other way, deflects towards the right. So same sort of example. We use different poles, we get different direction of the current in our coil. So we've looked at a lot of things here. We've got the number of coils affects the amount of current produced. We've got the strength of the magnetic field affects the current produced. We've got the rate of movement between the two affecting the amount of current produced. And then we have the strength of the magnet affecting it. So they're all the observations that Micheal Faraday put forward. Right, so there is a connection. We can go both ways. So Micheal Faraday did those experiments, and here is my graphic here to represent a quick summary of what he did. And he had our magnet, remember? And I had a little small coil of wire. Well, a coil of wire is called a solenoid, so I've just put a solenoid in there. I've suspended this one here, whereas in the video I was holding it, right? And we've got a galvanometer here, and that galvanometer measures small currents. And so if I get my magnet, remember when I pushed my magnet into the coil, we saw a deflection in the voltmeter there, telling us that there was a generation of a potential difference, and therefore a small current was flowing. So we saw that the main key points here, and let's write them out so it's very clear. The first key point is this relative. So we saw that relative movement of a magnetic field to a conductor causes or induces a current. So remember in the video we saw that when it was stationary, no current was produced. However, when I moved it, we had a current being produced, right? We had, and we're going to look at that more in the next video, but we had a current being produced there. And we also saw that this relative movement, we saw that there was a connection to how fast I moved it, right? The faster I moved it, the greater the deflection. The slower I moved it, the smaller the deflection. We're going to check that out in some subsequent videos as well. The second idea was there is that if I increase the number of the coils, we get a larger deflection. If I increase the strength of the magnet, I get a larger deflection. I wonder why. Well, we're going to find out why in the next series of videos, and when we relate it to Micheal Faraday's equation here. What else did we find out? Well, we found out that it doesn't really matter what I move, whether it's the coil or whether it's the magnet. It's this relative motion between the two. Okay, so it doesn't matter if I keep the magnet stationary and move the coil, or keep the coil stationary and move the magnet. So there's some fundamental key ideas there that we're going to come back and explore and relate to Faraday's equation, because that's exactly what you should be able to do. Not only should you be able to recall the different things that Micheal Faraday did, but you should be able to say, well, what variables did he change, what were the outcomes, and you should be able to explain all of that with his equation, which we will get to in later videos. I'm just providing a little taste tester here to show you that there is a connection between the magnetic field and the electric field, right? Both of those are connected, electromagnetism. And we're going to find later on in the course, in the next module, in fact, when we talk about Maxwell, James Maxwell, he started putting mathematics to describe the mathematics behind this connection. Anyway, that's it for this video. I'll see you in the next video. All right, before we go to the next video, I want you to check out more courses that we have here on our YouTube channel, which are just small snippets from the actual bigger courses that we have on theflipteacher.com. Of course, with all of our courses, we try to incorporate practical sessions. We have study cards, we have posters that you can print off and stick around your room and do a lot more. We have up to 68 or more videos per course. That's like 9 to 10 hours of material that really delve deep into the syllabus and looking at essential content, skills, mathematical manipulations, and a lot more. So if you like that, go over to theflipteacher.com and check it all out, and I'll see you in the videos.